So, good afternoon, students. This is Arvind, Assistant Professor, Department of Traffic, DBS, Kavali. So, in the previous classes, I discussed about some concepts like VS, voltage source converter, and current source converter, and the basic concept of current source converter. Okay, and three-phase full wave diode rectifier. And now in this class, I'm going to discuss thyristor-based converter operation. Okay, so let us start the session. So actually the thyristor-based converter has following operations like rectifier operation, inverter operation, valve voltage, commutation failures, AC current harmonics, and DC voltage harmonics. These are the contents we have for the thyristor-based converters. Mainly it consists of the rectifier operation and inverter operation. Actually, you know the rectifier operation and inverter operation in the previous sessions also. But today I am going to discuss first two operations. One is rectifier operation and the another one is inverter operation. And in the coming classes, I am going to discuss valve voltage, commutation failures, and AC current harmonics, DC voltage harmonics like that. So firstly, I will start with the rectifier operation of a thyristor-based converter. So coming to the rectifier operation of a thyristor-based converter. So actually, in the previous classes, that is from the discussions on the diode rectifier, that is in the previous class, from the discussions on the diode rectifier, it is easy to recognize that if the devices had a turn-on control, okay, the start of each commutation could be delayed. Okay, the start of each commutation could be delayed, and hence the output voltage reduced or even reversed at will. Okay, this is for the diode rectifier. Okay, next consider again the diode voltage waveform of diagram 4.4, and that means in the previous class I shown one diagram, last diagram. So that is the that indicates that represents the diode voltage waveform of that three-phase full wave diode rectifier operation. So that is when from instant T3 valve 3 becomes forward biased and is ready to commutate current from valve 1. So in the previous class also I discussed this one. And next, so this start of commutation could be delayed if the devices were thyristors. Okay, this start of commutation could be delayed if the devices were thyristors. And now I am going to show the diagram. It shows that the output DC voltage and phase current waveforms for the commutations delayed by an angle alpha. Okay, so I will show the two diagrams. One is for the previous case, that is for three-phase full diode rectifier operation, and now I will show the another diagram, that is the second diagram. It shows the output DC voltage and phase current waveforms of the commutations delayed by an angle alpha. Okay, so this is the first waveform. So this waveform is for the full three-phase full wave diode rectifier operation. So this one. So in that one we have the phase voltages, that is VA, VB, VC waveforms, and next we have ID, that means DC current waveform, and then we have phase currents IA, IB, IC. So here we have different time instants, that is from T1 to T6 we have different time instants. So at instant T1 to T2, the diodes 1 and 2 are conducting. That means valves. The valves 1 and 2 are conducting, and the current is flow from valve 2 to phase A. Okay, valve 2 to phase A. Out of phase A, out of phase A and valve 2. Okay, so at the instant of time 3, the valve 3 is conducting, and at the time of instant T4, the valve 4 is conducting. At the time instant of T5, the valve 5 is conducting. At the time of T6, the valve 6 is conducting. Like that, it continues from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Like that, the cycle repeats. So here the DC voltage equation is VD is equal to V naught by 2 into 1 plus cos gamma naught. Cos gamma naught. So here we have the current waveform. This is the DC current. It is a constant straight line. It is a straight line. Okay. Next we have the current waveforms IA, IB, IC. So these three are the phase currents. So actually in the three-phase full wave diode rectifier operation, I took a diagram. So it consists of, on the left side of the diagram, it consists of three-phase supply. That means three-phase terminals and with a neutral connection N. So on the right side we have this three-phase diode connection. That means we are using 6 diodes it will be numbered as 1, 2, 3, 4, 5, 6. Okay, and we have one inductor or reactor, the reactor device connecting to the DC supply. Okay, so here I am taking the IA current, IB current and IC current. So when IA current is flows, that is from 1 to 4, and IB current, that is the current flows from B to flows in the B when the conductor, when the valves 6 and 3 are in operation, are in conduction. And coming to the third waveform, so in this one the conduction of 2 and 5 is conducting, the diodes 2 and 5 are conducting. Okay, so like that the operation continues. And next, so this is the three-phase full wave thyristor based current source converter. This is the three-phase full wave thyristor based current source converter. Here thyristors without turn off control. Okay, here the thyristors without turn off control, that means it has the turn on capability, the thyristors. So in the previous class I discussed three-phase full wave diode rectifier. At that time same diagram I have been taken, but here same diagram here also I am taking, but in the diodes place I am placing the thyristors. Okay, in that one I used 6 diodes. In this operation now I am taking 6 thyristors. Okay, so it is numbered as 1, 2, 3, 4, 5 and 6. The upper thyristors numbers is 1, 3 and 5, and the lower thyristor numbers is 4, 6, 2. And on the left side we have the three-phase supply and the three-phase terminals we have. Those are namely A terminal, B terminal and C terminal, which consists of the neutral, transformer neutral connection, that is N, that is neutral. And on the right side that is the DC supply. So here we have 6 thyristors and one reactor or inductor is also there. Okay, in this one the DC current and DC voltage will flow. Okay, next these are the waveforms, same like in the diode rectifier operation. Here also we have different voltage waveforms and DC current waveform and phase voltage, phase currents waveforms also, AC current waveforms also here. Okay, but small difference is here the commutation is not delayed. Okay, so delaying, the commutation period is delaying, that means starting time is delaying. So here the short circuit current of the commutation process is not defined as before by. So here the short circuit current of the commutation process, the short circuit current of the commutation process is not defined as before by 2 into L into di1 by dt, that is equal to root 2 E sin omega t. So actually this equation is came in the previous concept also. Okay, here assuming now that the start of the commutation is at omega t is equal to alpha. So here the start of the commutation is at omega t is equal to alpha. So integration for omega t is equal to alpha and is is equal to 0 gives. So that is is equal to E by root 2 omega L into cos alpha minus cos omega t. And when omega t plus gamma and is is equal to id, it gives id is equal to E by root 2 omega L into cos alpha minus cos alpha plus gamma. So in the place of omega t I am substituting omega t plus gamma, and in the place of is I am substituting id. So that's why the equation becomes id is equal to E by root 2 omega L into cos alpha minus cos of alpha plus gamma. Okay, next, so from the equation, that is this equation id is equal to E by root 2 omega L into cos alpha minus cos of alpha plus gamma. So here the angle gamma can be calculated for a given value of angle alpha, and it is seen that the angle gamma decreases with increase in the angle alpha. So it is seen that the angle gamma decreases with increase in angle alpha. So this should be obvious, since the rate of rise of short circuit current is greater with the increase in the short circuited voltage. Okay, next equation for the DC output voltage. Okay, equation for the DC output voltage can be obtained by first calculating the output voltage with commutation angle gamma is equal to 0, and then subtracting the voltage lost due to commutations with gamma is equal to 0, the output voltage taking a 60-degree segment. So and is defined by, we have the equation that is the DC output voltage, that is Vd is equal to 3 by pi integral minus pi by 6 plus alpha to plus pi by 6 plus alpha root 2 e cos omega t d of omega t. So after integration, after integrating the above equation, finally we have the equation that is Vd is equal to 3 root 2 by pi into e cos alpha. So after simplifying this one, we have V naught cos alpha, that means 3 root 2 by pi into e, you will write as V naught. So V naught cos alpha. Next, so here where V naught is the output voltage corresponding to alpha is equal to 0 and gamma naught is equal to 0. Okay, that is from the last equation. And thus the output voltage with gamma naught is equal to 0 decreases as the cosine function of alpha. Okay, next, this means that with increasing alpha, the output voltage decreases slowly, first reaching 86.6% for alpha is equal to 30 degrees and 50% with alpha is equal to 60 degrees and 0 at alpha is equal to 90 degrees and negative for alpha is greater than 90 degrees. Okay, like that the alpha value is changing. Okay, and the output voltage also slowly decreasing. Okay. And next, now taking into account the commutation angle, so the area under each commutation is given by dou A is equal to 1 by 2 integral alpha to alpha plus gamma into root of 2e sin omega t d of omega t. So that is equal to 1 by root 2 e of cos of alpha minus cos alpha plus gamma. So this area represents DC voltage drop every 60 degrees. Therefore, dou V is equal to 3 by root 2 pi e of cos alpha minus cos alpha plus gamma. Okay, so this represents the DC voltage drop every 60 degrees. Okay, next, and Vd is equal to V naught cos alpha plus dou V. So from this one I am writing V naught by 2 of cos alpha plus cos of alpha plus gamma, or Vd by V naught. The per unit voltage is given by Vd by V naught is equal to 1 by 2 cos alpha plus gamma. So from the two equations we will write dou V is equal to 3 omega L by pi into Id. So that is from the equation 4.11 and 4.12. So it will give Vd is equal to V naught cos alpha minus, in the dou V place I am substituting 3 omega L by pi into Id. Okay. So as would be expected, the voltage drop for commutation is the same. That means 3 omega L by pi into Id for any delay angle. That is, the commutation voltage integral is always the same for the same current. Okay. Next, thus a converter output voltage for any value of delay angle alpha. Okay, here I am considering the converter. So thus a converter output voltage for any value of delay angle alpha, DC current Id and AC voltage E can be obtained from the previous equation. So from this equation, that is Vd is equal to V naught cos alpha minus 3 omega L by pi into Id. So from that equation, we will get AC voltage E and DC current Id and a delay angle alpha of the output voltage, that is Vd. Okay, and is represented by a simple equivalent circuit of a variable DC source in series with an equivalent resistor, that is shown in this diagram. So this diagram is the equivalent circuit for a current source converter. So actually it consists of a equivalent circuit of a variable DC source. So if we look at this diagram, if you observe this diagram, on the left side we have the variable DC source. Okay, it is in the box. Okay, it is in the box. So here I am indicating with the arrow mark, that means it is a variable DC source. Okay, so it is in series with the equivalent resistor, that is 3 omega L by pi. It consists of the value, that is 3 omega L by pi. Okay, so this resistor in turn is a reflection of reduced lagging reactive power on the AC side. Okay, on the AC side. And next, so in per unit terms, assuming V naught as 1 per unit, V naught, inductance omega L in per unit as XP is equal to omega L into I by E by root 3. So then combining those two equations gives a per unit value of the DC output voltage, that is written as Vd by V on is equal to cos alpha minus XP by 2. So that means from this one we say converter transformer plus the system impedance is 20% and inductive, that is 0.2 per unit. Okay, the DC voltage will drop by about 10% from no load to full load. So here the DC voltage will drop by about 10% from no load to full load, and the power factor on the AC side will drop correspondingly. Okay, so if it is assumed that Vd is equal to V naught cos phi, then the power factor cos phi is approximately given by, so Vd by V naught is equal to cos phi, so that is equal to cos alpha minus 3 omega L by pi into Id. So from this one we will write 1 by 2 cos alpha plus cos of alpha plus gamma. So it will treat it as 4.17 equation. Okay. Next, so up to now we discussed about the rectifier operation of a thyristor-based converter, and now I am moving to the inverter operation of the thyristor-based converter. So here firstly we will consider converter operation assuming zero commutation angle. So here we are considering the commutation angle, that to 0. That is for the assumption, that too for the assumption. Okay. So here I am considering first converter operation assuming zero commutation angle. So here I will show the diagram. It shows that the output voltage with varying delay angle. Okay. So in that one we consist of the two diagrams. That too, the first diagram is for the normal rectifier operation with a small delay angle alpha and shows the positive output voltage by inclined hatched areas. Okay, and one more diagram is also there, that is B. So from the diagram B is for the diagram B is for the case when the delay angle alpha is increased, when the delay angle alpha is increased beyond 60 degrees, and it is seen that there are some negative areas corresponding to the angle in excess of 60 degrees shown by horizontal hatching, that means horizontal lines. Next, if the DC load on the rectifier was resistive, that means if the DC load on the rectifier was resistive load, its operation would be discontinuous because conduction would not occur in the negative direction. Okay, conduction would not occur in the negative direction. Next, this is the diagram we have. So the first two waveforms gives the rectifier operation. Okay. Next, third diagram gives the zero DC voltage, and finally we have the full converter operation, full inverter operation. So these are the horizontal hatched areas we have fully. So this is the rectifier operation A and B, and third one gives the zero voltage, and finally we have the full inverter operation. Okay. So these are the waveforms we have, all are sine waves, but we have some hatched areas in between. Okay, first waveform is completely consists of the hatched areas, and second waveform consists of some horizontal hatched areas and some dotted hatched areas, and next we have the third diagram will also consist of the dotted lines and horizontal line hatched areas, and finally full inverter consists of totally the upper section consists of the horizontal hatched areas and the lower section consists of all the dotted hatched areas. Okay. Next, but with a large inductor, the difference between the positive and negative areas will average out to a resultant output voltage on the DC side. Okay, here we are using a large inductor. So here the difference between the positive and negative areas, that means positive side and negative side of the waveforms, will average out to a resultant output voltage on the DC side. So at 90 degrees delay, the positive and negative voltage areas become equal and the average voltage is 0 as per the previous equations, that is 4.11 equation. So that too from the Vd is equal to V naught cos 90, that is equal to 0. And as the delay angle is further increased, that is from 90 degrees to above, okay, as the delay angle is further increased, the average voltage becomes negative, and at 180 degrees the negative voltage becomes as large as that for the rectifier with zero delay angle. Okay, next it is assumed that for an inverter to operate and feed active power into the AC system, there is another source of DC power which causes the DC current to flow in the same direction against the converter's DC output voltage, thus feeding DC power into the inverter. Okay. Next, so actually an inverter cannot be operated at a delay angle of 180 degrees because sometimes the angle gamma is needed for the commutation of current, and further time that is at the angle 80 is needed for the outgoing valve to fully recover, that means turn off. Fully recover means the fully turn off before the voltage across it reverses and becomes positive. Okay, up to now we take this inverter not operated at a delay angle of 180 degrees because of these reasons, and otherwise the outgoing valve will commute the current back and lead to a fault known as commutation failure. So this is also one of the concept in the thyristor-based converter. I will discuss this commutation failure concept in the next classes. Okay, so here I will show the one more diagram. So the diagram shows the inverter operation with an angle alpha, so which is somewhat less than 180 degrees, which is somewhat less than 180 degrees. Why? Because an inverter cannot be operated at a delay angle of 180 degrees. That's why here it is somewhat less than 180 degrees. Okay, and also shown are the valve currents and various angles dividing the range of 180 degrees angle into the delay angle alpha, commutation angle gamma, safe turn off angle delta, and angle of advance beta is equal to gamma plus delta. Okay. So this is the diagram I am discussing. So on the left side we have the thyristor connections. Here we are using 6 thyristors in series, and next we have the inductor. So it is for the DC side. On the AC side we have the 3-phase connection. So it consists of 3 terminals A, B and C, and it consists of a neutral connection also, that is N. Okay. So it will give the inverter operation with an angle alpha which is less than 180 degrees. Okay. And next these are the waveforms. Okay. First is for the 6-pulse thyristor converter operation, and next is for the voltage and current waveforms. The first waveform gives the 6-pulse thyristor converter operation. So that means the voltage and current waveforms it will give. So here also I am taking first waveform. It takes the voltage waveforms for the 3 phases A, B and C. A, B and C. Next we have the currents, DC current waveforms and phase currents, IA, IB, IC currents waveforms we have. Okay, here we are using the 3 angles gamma, beta, delta. Okay, so these are the waveforms for the 3-phase fully thyristor-based converter, means current source converter in the inverter operation. Okay, next, for safe operation, angle delta must not be less than 180 degrees. So for safe operation, angle delta must not be less than 180 degrees. Often for convenience, inverter equations are referred to in terms of angle of advance beta, commutation angle gamma, and margin angle delta. So all the equations derived earlier in terms of alpha and gamma still apply, and if preferred they can be obtained by substituting alpha with pi minus beta or pi minus of gamma plus delta. They are not included here. Okay, these are all not included here, but I will show one more diagram. It shows the phasor diagram of AC voltage and current indicating the range of operation of a line commutating converter with the hatched area. Okay, so the figure shows the phasor diagram of AC voltage and current indicating the range of operation of a line commutating converter with the hatched area. So it shows that the operation is limited to 2 quadrants. So the rectifier operation limited by the commutation requirements at alpha is equal to 0 and the inverter operation limited. Okay. All the other end by the commutation and valve recovery requirements. Okay. So this is the diagram. This is also known as operation zone of thyristor-based converter. So here the operation is only limited for the first two quadrants only. So these two quadrants consist of the hatched areas. Okay, and the remaining two is empty. Okay, so the operation mainly in these two quadrants only. Total we have the 4 quadrants, but here the operation the continues in the thyristor-based converter. It only under the 2 quadrants only. Okay. So next, throughout the range, it consumes reactive power, which can be calculated from the equations for the power factor. There is 4.9 and 4.17. We have to calculate the power factor. So for a given current and voltage, okay, for a given current and voltage, the active power decreases and the reactive power increases, with increase in alpha from 0 until it reaches 90 degrees minus gamma by 2 when the DC output voltage reduces to 0. So at this point the active power is 0 and the reactive power is at its maximum. In fact, a line commutating converter is also used as a static wear compensator. Simply we'll call it as SVC, to consume controlled reactive power. Okay. So at this point the active power is 0 and reactive power is at its maximum value. And line commutating converter is also used as SVC, to consume controlled reactive power. So this is done by operating the converter with a short circuit through a DC inductor on the DC side and controlling the DC current flow by controlling angle alpha. And it should be noted that the equations above represent the rectifier and inverter conditions for the commutation angle gamma less than 60 degrees. If this angle is exceeded, that means above 60 degrees, the operation is no longer represented by the same equation, since two commutations will take place simultaneously. So this situation is not likely in steady state conditions, but may occur during high DC fault current. So it should also be noted that operation with delay angle alpha less than 30 degrees and commutation angle gamma greater than 60 degrees simultaneously is not possible here. Okay, next. So if for say alpha is equal to 0, the current is so increased that the corresponding angle gamma is greater than 60 degrees, then the firing of the valves will not take place at alpha is equal to 0, but will be automatically delayed so that gamma is equal to 60 degrees. So this situation continues until alpha is equal to 30 degrees and gamma can be increased. So under such conditions, the equivalent commutation resistance in the diagram and 4.6 becomes 9 omega L by pi, 3 times the normal value of 3 omega L by pi, that is 3 times to the first value. Okay, thank you for watching this one. Okay, so in the next class I'm going to discuss the remaining one: valve voltage, rectifier, valve voltage, AC current, harmonics, commutation, position, DC voltage harmonics, like that. Okay, thank you.